What's up, guys? So a little video on back titrations, a topic that people find super hard. Hopefully this will make things a bit clearer. So what is a back titration? Essentially, it's an indirect method for working out the concentration of something, or the moles of something. Now, what I liken it to is being given £10 by your mum to go to the shops to buy some milk, right? And you come back with £8.20 change. Very, very simply, you're going to work out how much the milk cost by doing the £10 minus the £8.20, right? So there we get to £1.80. This is exactly the same, all right? We can't directly work out the concentration or the moles of something, so we almost work out the change. We work out what's left over. Best way to highlight this is to go through an example. So that's what we'll do. Limestone, mainly calcium carbonate. Now, this is often going to be done with carbonates because carbonates are quite difficult to neutralize with an acid. All right. So here we've got a neutralization here, but we're going to be reacting this acid with it over a long period of time. So it might be left overnight, something like that. So we can't just measure our final drop and see what colour, see when our indicator changes colour. We've got to leave it overnight, see how much HCl, do loads and loads of HCl, and see how much we have left over. That's essentially the process, right? So, calcium carbonate. Student wanted to find out the percentage, what percentage of some limestone was calcium carbonate. 1 gram sample. So we've got a 1 gram sample of limestone allowed to react with 100 centimetres cubed of 0.2 mole per decimetre cubed HCl. The excess acid required 24.8 centimetres cubed of 0.1 mole per decimetre cubed NaOH. So this is essentially what we're doing to measure what's left over. In a back titration, calculate the percentage. So let's start putting that together. So we're talking about titrations here. We've got C, N, V, C, N, V. And we can start filling out our information. So we've got 100 centimetres cubed of HCl. We've got 0.2 moles per decimetre cubed. So we can work out the moles we have initially. So we've got C, N, V. So we're going to do concentration times volume. And there we get to 0.02. So we've got C times V equals 0.02. So this is, if we use our analogy up here, this is our £10, right? This is our excess. We need to work out what our change is. So to do that, we look at the information from our titration, right? So here we're told we've got 24.8 centimetres cubed of 0.1 moles per decimetre cubed of NaOH. We've got 24.8 over 1,000, 0.1. So very simply, we do C times V again to work out what our moles of NaOH is. And there we get to 0.00248. We've got a 1-to-1 molar ratio, so we times by 1, right? To work out our moles here. So we've got the same number. This is our change. This is what we have left over of the HCl. So in our analogy here, this is our £8.20. So we need to work out what we have here. So minus 0.00248. And there, the value we get to is 0.01752. Now we look at our molar ratio here. We've got 2 to 1, in which case we need to divide by 2. So our moles of CaCO3 are 0.00876. So we've got our moles. That's not what our question asked though, right? We need our percentage calcium carbonate in 1 gram. Where's our 1 gram? 1 gram. So now we start thinking about our mass Mr. Mole. We've got our moles. Let's work out our MR. MR is equal to, we've got 40.1 for calcium, carbon's 12, oxygen 16. So we've got 1 lot of 40.1 plus 1 lot of 12 plus 3 lots of 16 gets us to 100.1. Nice. Then we do, to work out our mass, we're going to do our MR, which is 100.1, multiplied by the moles we worked out, so 0.00876, and there we get to 0.877 grams. Our final answer, we need the percentage purity. It's a bit like our percentage yield, so our actual mass, 0.877, divided by the mass of the whole thing, which was 1 gram, times by 100. And there we get to 87.7%. Circular answer. Couple of things we might need to be careful of. Sometimes we're not going to titrate the whole solution down here. What we're going to titrate is, say, 25 centimetres cubed. So sometimes when we're moving from one place to the other, we might be timesing by 10, timesing by 4 in this case, if we took 25 centimetres cubed. That's one extra step that we might need to be a little bit careful of. This is the question I want you to give a go. I'll be honest with you, it's the only past paper question I've managed to find on this subject. It's not commonly asked, but it's good practice to really embed our AS level titration knowledge, and it can be asked. So give that a go. Let's, for now, go back to what we did last time. So let's see. Let's answer this. M, group 2 metal. We've got MnO3, 2 lots of that. 0.32 grams. Heated strongly completely. We've got our values. So, as always, P, V, N, R, T. Pressure, we're told, is 101,000. That's in pascals already, so we don't need to do anything about that. 225. But that's centimetres cubed, we need metres cubed. So we need to times that by 10 to the minus 6. N, we need to work out. Our equation for that is PV over RT. R, we're told as always, 8.31. And temperature, we're given here 450. But that's in degrees centigrade, so we need to add 273. We get to 723. We put these values in PV over RT, and we get to 3.78 times 10 to the minus 3. That's our moles. Now we need to use our moles and our mass to work out our MR. So we've got mass Mr. Mole again. So we do our 0.32 divided by our 3.78 times 10 to the minus 3, and we get to 211.9. Now that is the MR of MnO3 2. Now we need to work out the identity of M. So for that, MR of M, or we need to work out the MR of NO32. So there we've got 2 lots of 14 plus 6 lots of 16. That gets us to 124. So the MR of M equals our 211.9 minus 124. And then we get to 87.9. 87.9, we look down. It's not exactly 87.9, but that's close. So this is our number. It's strontium. M is strontium. Hope that's helpful. Give the other question a go and I'll answer it at the end of next video. Happy revising.